The shunt regulator is used in circuits where we're going to need a supply that has the ability to deliver a large current value. In other words, my load resistor will have a small resistance. When we look at the outlay of the circuit, our input voltage over here connects from our filter. That connects in series to my series resistor, and then the circuit becomes a parallel circuit. The first branch of this parallel branch is the output resistance. The second branch is my transistor, the emitter collector junction of the transistor. The third junction is my Zener diode connected in reverse bias, and then the base emitter junction. Now if this is a silicon transistor, we will develop 0.6 volts on that base emitter junction. So the output voltage technically is equal to 0.6 volts plus my Zener voltage that I have over there. Now because of the configuration of the transistor and the Zener diode, that output voltage will have a constant voltage across itself. The excess voltage, which I've marked in red, that is the size of the voltage that I will see on my series resistor. We need to remember that the only value that is important when doing the calculations is the maximum voltage that we will develop on the series resistor. To simplify this circuit, we're going to look, that's V in, that's going to connect through my resistor, that connects then to my Zener diode, which then connects to my 0 volt or my negative supply over there. Now my output in essence is this voltage that's going to develop on the Zener. So that's V out, that we know connects to the base collector junction of the transistor in order to operate as a regulator. Now we can see from this that the voltage that develops on the Zener diode is equal to the voltage that is going to be on the output. My input voltage, we can see, is a combination of the output voltage plus the value of my series resistance voltage. The current flow in total is going to equal the load current. In other words, if I have a resistor over there or a resistance over there, the current that flows through my load plus the current that flows through the Zener is going to be my total current. Therefore, the power that develops or is required for the Zener diode is the product of the voltage of the Zener diode multiplied by the Zener's current. So the size of my series resistor, in other words the required power rating of that series resistor, is the product of the series resistor's voltage that develops when my input value peaks multiplied by the amount of current flow through that Zener diode. I can also convert this formula into I squared times the value of the series resistor, and that's PRS. That's just the different power formula for this scenario.